Thanks for the introduction. I'm Erika. I'm a postdoc in the Scalable Solvers group, working with Chao Jing. Today, I'll actually be talking about different projects that we're working on parallel estimation of excited states using tensor trains. So the motivation is that we want to build tools to help scientists better understand complex molecular dynamics. So an example of this are transition metal compounds, which act as catalysts in many reactions. So, for example, this vanadium cluster is used in plastics or rubber synthesis to improve yield. on the right is an iron sulfur cluster that's like the key component of nitrogenase, and that is a biological enzyme that helps with nitrogen fixation. So you could better understand these reaction mechanisms when you could potentially design catalysts that help improve the efficiency of manufacturing these chemical compounds. However, even though these molecules only involve tens, 20s of atoms, the system size is actually quite large because there are many, many electrons and many orbitals that are interacting. Furthermore, we're interested in dynamics, so we can't only look at the ground state configuration. We also have to look at the excited states that the reaction might go through. To make this even more challenging, oftentimes in a small energy window, there are many, many excited states. So it's hard to target a specific one to study. So we're looking at this problem using tensor trains, and we'll focus on two main methods. First is excited state DMRG, which is sort of the standard method these days. So DMRG is a local update method, meaning that we have our eigenstate represented as our tensor train. That's sort of the colorful diagram at the bottom. And only two of the tensors are updated at a single iteration. So so in this example, the pink and the orange tensors are held fixed, and the blue tensor is updated or optimized. And so because the method only does these local updates, its computation at all costs is relatively cheap. However, the calculation is less accurate, and there's no proof of convergence. Furthermore, if we wanted to estimate multiple excited states, this would have to be done serially. And so I won't go into this method anymore. Since it's a relatively standard method, I use this open source package called Block2. The second method that we look at is subspace iteration. So this is a global update method, meaning that all of the tensors in the tensor train are updated simultaneously. So at the bottom, I have a diagram representing matrix vector multiplication in the tensor train format. So the gray row tensors on the top, it's matrix in the tensor train format. And then the row of red tensors on the bottom is the tensor train vector that we're multiplying the matrix to. And the output of that is going to be another tensor train vector, and it's shown in blue. And during this procedure, all of the tensor cores are updated, so all of them are colored blue. And so this is the global updates, even though it technically have the same scaling with respect to rank as DMRG, it will be more expensive in practice. However, the methods are going to be more accurate, and we can guarantee convergence to the correct solution. Furthermore, the subspace iteration method that we'll work on can be parallelized. Okay, so the subspace iteration method was actually developed in a group. Alec was the lead on this project. And we looked at using this method for computing ground states and low-lying excited states of simple toy models. So the method is actually quite simple. Let's say we have our Hamiltonian or our operator A in the tensor train format. We also have initial guesses for each of the eigenstates, which are represented by V sub 1, and so on. And let's say we're interested in n excited states. Then the procedure is as follows. We first perform power iteration to obtain estimates of the eigenstates. And then we do a Rayleigh-Ritz procedure to orthogonalize those eigenstates. Then we repeat those two steps iteratively until we get convergence. So in the next set of slides, I'll go through each of these steps in more detail and talk about how we can target energy states, and also parallelize this method to reduce runtimes. So the first step, power iteration. So the yellow box is the expression that we're working with. we see that we're applying some polynomial expression of A to each of the vectors B. So the idea of power iteration is that as you apply this matrix A to any random vector, you'll eventually converge to the dominant eigenstate. But you can also design a polynomial expression of multiple powers of A and to help you select a specific eigenstate of interest. So on the right is the blue curve. That's an example of a polynomial filter where we're selecting eigenstates in the middle of the spectrum. And this happens to be a polynomial of degree 12. Another, the last part of this expression is the T sub r, and this represents the low rank integration that we need to perform because we're working with tensor trains and we want to maintain a low rank approximation so that the computational cost remains feasible. And so this low rank approximation introduces an error, but fortunately, it was shown in the original paper that we can tolerate some amount of error depending on the separation of eigenvalues over routine. Finally, one last thing to point out is that all of these operations act on each of the separate vectors Vj separately. So it's easily parallelizable. We can assign one vector to each process and then compute these in parallel. The second step is a Rayleigh-Ritz procedure. So this is in this procedure, we want to create a reduced eigenvalue problem. And this involves computing the overlap and then the expectation value between all of the different vectors from the previous step. And so this required, this cost scales like m squared, where n is the number of states. And we can parallelize this to scale linearly with m. However, we do need a lot of communication because we need the vectors from one process to be mapped or to be communicated to another process to compute these values. Fortunately, when testing some scaling tests, we found that this communication is actually quite negligible compared to most of the other computational cost. So we ran some simple tests. In the first one, we fixed the number of excited states per node. So there are 2 excited states per node, and then we increase the number of nodes. In the plot, there are 2 lines. The orange line corresponds to a test that's a larger size than the blue line. In both cases, we see that the relative runtime increases linearly as we increase the number of nodes. The overhead with the larger test is less than that of the small test, and that's because there's more things that need to be computed, and the communication is less heavy. The second test, we fix the number of excited modes and then fix the number of excited states and increase the number of nodes. And in this case, we expect a linear decrease in runtime. So in all of these tests, we do see that the green is the largest test case. In this case, the overhead is the largest because there's more information that needs to be communicated between the nodes. But overall, relative to other computational costs, the communication is relatively small. So finally, we look at the performance of subspace iteration compared to DMRG. So in the top 2 rows, we look at low-lying excited states. So both DMRG and subspace iteration give relatively accurate results. The error in the subspace iteration is slightly lower, but the runtime per excited state is significantly larger than DMRG. However, if we move to higher energy states, in the bottom 2 rows, we see that both DMRG and subspace iteration struggle, but subspace iteration is able to obtain results that are more than an order of magnitude more accurate. Even though the runtimes are quite large, the saving grace is that we can compute these states in parallel. Okay, and with that, I've shown that we have a method that can systematically approximate excited states, and these excited states can be estimated in parallel. In the future, we'd like to further optimize these methods. So there are different parameters that we can play with, particularly the degree of the polynomial. we can also perhaps choose a better initial guess to start at. And then we'd also like to improve the practicality of these methods by testing on more complex molecules and also try to target specific states based on whatever symmetries we're interested in. With that, thanks for your attention. I'm happy to take questions.